Hey, how's it going? I'm gonna try to wing it. Wish me luck. We're gonna talk about acid-base reactions and buffers. All right. Like I said, I'm gonna wing this. I'm gonna show my screen, and hoping that I make some quality decisions. Right. Oh, guys, let's go ahead and change the color of our backgrounds today. Let's see how these colors look. Is that appropriate? Oh, yeah. Oh, yeah. All right, guys, let's get started here. We are talking about acid-base reactions and buffers. All right. Might not be one of our shorter videos. Let's first look at a strong acid, strong base reaction. All right, we know that the net ionic equation will be this. All right, I'm just going to write H2O this time. That will be the net ionic equation. We could calculate the pH. Say if it was initial, right? The initial pH would be whatever the pH was of the acid. You kind of think of we're adding acids and bases together, right? So if I just have an acid, the initial pH is the, right, pH equals negative log concentration acid. And remember, we have 100% dissociation here, right? Now, if I have added some acid or some base to my acid, I would need to first determine the stoichiometry of that, right? So, I might have a volume and a molarity. So we could keep it simple. Let's say that I have 1 liter of 1 molar NaOH. That equals 1 mole of NaOH, right? And I have 2 liters, I'm just making these numbers so simple, of HCl. That makes 2 moles of HCl, right? So I would need to do that. I would need to know how many moles do I have, because that's the reaction. And it's not in terms of concentrations, it's in terms of moles. So, let's say that I had 0.5 liters and it was of 1 molar NaOH, then we see that we would have 0.500 moles. So we would need to get our moles of hydrogen and hydroxide ions. Let's say that initially this was 3.00 molar. Oops, goodness gracious. Let's say that we did our calculations and we ended up having 4 moles of hydrogen. Usually they're much smaller numbers, but who cares? And let's say that we added 1 mole of hydroxide. Well, we see that this would be our limiting reactant, and we would be left with 3 moles of hydrogen, right? We would need to divide that by the combined total volume of acid and base, right? Because we've added them together, right? And when we divided that, that would give us our concentration of hydrogen. And then we would just simply get the pH is equal to the negative log of that hydrogen concentration, right? So we need to get the moles. We need to, right, we get moles of both acid and base, right? We do the stoichiometry. We're going to call that the stoich ice chart. Divide by total volume in liters to get concentration. And then you would get the negative log. Solve for pH. Concentration equals pH, okay? Now, if you look up here and let's say that this, right, let's change those numbers. Let's say that H plus OH yields H2O. Why is he way over here? Let's move him over, guys. He's a little by himself. You know, we said that we initially had 4 moles of this. Well, maybe we added more base, right? Maybe we added a lot more base. Then this becomes the limiting reactant. And you see that 2 moles would remain, right? And we would then divide that by the total volume. We would get the concentration of OH. We could then get the POH. We could then get the pH. Okay, so strong acid, strong base are really simple. Now let's change it up and let's look at a weak acid. All right, we're going to call that HA, and a strong base. And this is not quite so simple. Our strong base will be hydroxide. So what we're doing is we're adding these 2 solutions together, right? Initially, right, we only have HA. And guys, what we're concerned with here is the pH, right? Getting the pH for the most part. All we have is HA. So the pH is simply equal to, right, we need to write the dissociation equation. And if you see this as easily as I do, we will have a concentration here, 0, 0, minus X plus X plus X, concentration minus, let me rewrite that. We would then down here have whatever that concentration was, minus X, X, X. We would assume this term to be negligible. And we see that Ka would equal X squared over the concentration. We would solve for X, and P, we would solve for X. Hold on, right? Solve for X, negative log X equals H plus pH equals negative log H plus. Okay, that's what we would do initially. So if we only have HA, we're simply going to do this. Let me change my color there, guys. We're simply going to use our Ka to solve for X. And then we will plug, you guys see this, right? Hold on, that does not belong there. X equals H plus, I'm sorry about that. Okay, so what happens if we start adding some base, right? So that was how we would get the pH initially, right? That's how we would get the pH initially. We would just have the weak acid. Now, how would we get the pH after some base was added? But not to the halfway point. Okay, so I'll try to explain. I don't know where we are in this learning, but we may not have talked about the halfway point yet, but we can figure that out. So what we have is our weak acid. We are adding hydroxide to it. We are getting our conjugate base and forming water. We're not concerned with the water. Now, we have a volume. This time we'll have 0.100 No. Oh, yeah, I could have kept that. We'll have 1.0 milliliters of a 2.0 molar HA, and we can see that that is 0.20 moles of HA. We are going to, in this step, now I'm gonna figure out how much hydroxide we're going to add. Well, if we are, I want you to understand what I'm trying to figure out. If we are not to the halfway point, so the halfway point would be half. So if we're not quite there, we're anywhere below that. So let's make it 0.50 moles. Now, my question to you is, if the concentration is 1.0 molar hydroxide, because you might see questions like this, and I need to have 0.50 moles, then what volume have I added? Well, 0.50 moles, according to our molarity, there's 1.0 mole for every 1 liter. That's 0.5 liters. That's 1, 2, 3. That's 500 milliliters. Okay? You should be able to figure that out. Let's keep going. Okay, 0. So, oh, whoa. I need this to be 0.05. So everything just changed a little bit. It can't be greater than. We need to be less than 0.05. So this became 0.05. So this became 0.05. So this became 50. I thought 500 was a little big. 50. Limiting reactant, add that right here, right? 0.20 minus 0.05, 0.05. Now, what we have, please listen here. These are moles. What I can actually solve for this right here, so I need to do that. 0.20 minus 0.05 is 0.15. All right, moles and moles. There's a lot to this lesson. I apologize. Now, what we have here is the presence of a weak acid and its conjugate base. When that happens, first of all, we have a buffer solution. It's not ideal yet, but we do have a buffer solution. I will explain that more later. For the most part, a buffer solution resists the change in pH. All right. And I know I have a buffer solution because it contains a weak acid and its conjugate base. Okay, that's cool. That's cool, no big deal. And it's conjugate base. So I once again need to get my pH. So what did I do? I got my moles, right? I got my moles. I did my stoichiometry ice chart. I'm going to get my new molarity by dividing by the total volume, right? So that's both going to be divided by, I'm sorry, but I can't do that color. So let's go with green here. We're going to divide by the total volume, which, as you see, we're going to stick with white, is 50 milliliters plus 100 milliliters, which is 0.150 liters, because it's 150, so it's 0.150 liters. And we will divide that. And when that, right, we got our moles, we did the stoic part, we're dividing by the new concentration to get our new molarity, all right? And what we have here, boom, boom, oh, that looks like 1.0 molar. And I apologize, but I'm not going to do that in my head. 0.05 divided by 0.15 equals 0.33. Okay, so what happens is we're not done. We did, once again, we did the, we got the moles, we did the stoic part, we got the new concentration. Because we've got a weak acid and its conjugate base present, we will have a new equilibrium position must be established. Okay, so what are we going to do? Well, we've got options, but we haven't talked about all of them yet. So I'm going to give you this option. I'm going to give you HA, H plus, A minus, Ka equals some number, right? Look at your concentrations. We've got 1.0 and a 0.33 and a 0 minus x plus x plus x, 1.0 minus x, x, 0.33 plus x. These x terms will be negligible. Ka will equal 0.33 over 1.0 times x. X will equal H plus the pH. Whoa, my head was thinking about a different problem that we might do later and how long this video is, will equal the negative log of H plus. Okay? We're not stopping. You might want to take a break, but we've got more to do and I'm going to keep on going for now. Okay, so we have our same system, HA, weak acid, strong base, conjugate base, water at halfway point. So we have, let's go back up here, 100 milliliters, 2.0 molar, right? 100.0 milliliters, 2.0 molar HA. We said is 0.200 moles of HA. We're using a 0.100 molar NaOH. If we're at the halfway point, we will have half as many moles. You should be able to figure that out yourself so that if I need this many moles of OH, what volume did I use? Is it a 1 molar? It's 1 molar, sorry. Right, so I need to be able to figure out the volume because remember, I need to get my new concentration. So you need to be able to figure out what volume you need to get to the halfway point. We said that 1 mole is 1 liter, so that's 0.100 liters. That is 100 milliliters, twice as much as last time. Okay, so we have 0.2, sorry, 0.2 moles of this. We've gotten to the halfway point. It's 0.100 moles. We do not have any. Minus 0.100, minus 0.100, plus 0.100. 0.200, 0.100, 0.100. Now, we still have some acid and some conjugate base. They are in a perfect 1-to-1 ratio. This is an ideal buffer. It will resist the change in pH upon addition of an acid or a base. All right. The acid will the acid, if added, would react with this. The base, if added, would react with this. Both are present. The acid has something to react with. It won't go in the solution. The base has something to react with. 1-to-1 ratio of weak acid to conjugate base is ideal. How do we get the pH at the halfway point? The pH is equal to the pKa. Therefore, pH equals negative log Ka. Boom. Let's do another one. Now let's say at the equivalence point. All right. Once again, HA plus OH yields A plus H2O. We said we have a 2.0 molar. We have 100 milliliters of it. We said that's 0.200 moles of HA. So at the equivalent point, we need 0.200 moles of OH. It is a 1.0 molar. So the volume we will need is 1 mole for every 1 liter is 0.200 liters is 200.0 milliliters. We've got 0.200 moles of this. We've got 0.200 moles of this. So we will neutralize all of our acid and have none left over. We will use all of our hydroxide and we will gain our conjugate base. Will be the only thing present at that given moment of time. All right. So what we have, oh gosh, get rid of that. What we have here is the at EQ conjugate base only species present. It is the conjugate base of a weak acid. It has basic properties. It will participate in equilibrium, needs to find its equilibrium position in water. All right, needs to find EQ position in water. Okay, now we need to get the new concentration, right? So find concentration. That's going to be equal to the 0.200 moles. Let's, right, moles of what? What are we doing? Divided by the total volume, that's 200 milliliters plus 100 milliliters is 0.300 liters. That, what's a third of 0.2? 1.6, 0.2 divided by 0.3, oh, 0.67, stupid me, 0.67, 667, I guess, if you want. We're not, you know, in a problem like this, you're not your focus right now. 0.667 molar A. We need to write the reaction with A in water. Well, A is the conjugate base. What do bases do? They take hydrogens. All right, so there's going to be a tug of war. How much of this do we have? 0.667. 0, 0. Minus X plus X plus X. 0.667 minus X, X, X. This is a KB. So KB equals KW divided by KB. Oh my gosh, KW divided by KA, right? This is a base reaction occurring right here, right? This is basic in nature. If you don't see it, This is very, you can't see what I'm doing because the colors. Right? This is a basic equation in nature. The A is acting like a base, so we need a KB. So we must solve for KB. We then can say that KB is equal to x squared over 0.667. X is equal to hydroxide. POH equals the negative log of the hydroxide. And the I apologize for that. And the pH is equal to 14 minus the POH. For real though. Now, if we were to continue and be beyond the halfway point, or the equivalence point, right? We're way past the halfway. Beyond equivalence point, right? HA plus OH yields A plus H2O, right? We had 0.2 moles, 0.200 moles. Let's say that this was 0.300 moles. 0.200 moles minus 0.200 moles plus 0.200 moles. We're almost finished here, right? This turns into 0.100 moles, and 0.200 moles. Well, at this point, guys, we've got two things going on. I'm glad we continued this far. We've got hydroxide present, and we've got A present. Okay? Well, the hydroxide is going to dominate. This will dominate the pH. The pH from this point on. Okay? We do not need to consider that conjugate acid or base and his properties of causing things to be basic. It will be negligible compared to what the hydroxide does. So I know that blue is hard to read, but it says this will dominate the pH from this point on. Let me change my color here. We will get the new concentration, get the concentration of OH by dividing by total volume. And then remember that we would get the POH equals the negative log of OH. And then we would say the pH equals 14 minus POH. I mean, or you could go, right, you could say that H equals 1.0 times 10 to the negative 14th over OH, and then just say that the pH is equal to the negative log of H, right? So you've got some options there. Now, if this was a weak base and we were adding acids, I'm going to add it like that, or it could go like this, okay? We would have HB plus HB plus water, okay? Over here, there is no water. And we would do the exact same things, okay? But at the equivalence point, right, we would see this. 0 minus x, minus 4.00 minus 4.00, 0, 0, plus 4, 4, right? We would then get the new volume. This would need to find its new equilibrium position. So we would need to solve for what that equilibrium position would be. So we would write HB yields H plus B minus. We would need a Ka, right? We would put our concentration here, 0, 0, minus X, plus X, plus X, concentration minus X, X, X. We would probably have a Kb. We would need to make sure we have a Ka because this is an acidic equation, X squared over the concentration, X equals H, and then we would get the negative log of H to, in fact, have our pH. I think we're going to stop there. We'll talk.